All right, let's dive right into this explainer. We're embarking on what is, quite frankly, the ultimate cosmic thought experiment. Today, we're exploring what actually happens when you cross the absolute ultimate threshold in the universe, the event horizon of a black hole. We're going to look closely at the math, the physics, and the completely mind-bending reality of the abyss.
You know, for decades, sci-fi has basically drilled into our heads that falling into a black hole is an instant death sentence, right? Just a one-way ticket to being crushed into oblivion. But recent physics research and mathematical models suggest a completely different and deeply fascinating reality. So, throughout this explainer, we are going to shatter those pop culture myths and take a visceral, step-by-step dive right into a supermassive black hole. Section 1. The Spaghettification Myth.
So, as we start our descent, we've got to confront the most famous and, honestly, most misunderstood black hole concept out there. Let's talk about why you actually might not get crushed. If you were to fall into a standard, non-spinning Schwarzschild black hole, then yeah, that fatal stretching is absolutely inevitable. Gravity pulls harder on your feet than on your head, and you are stretched into a literal string of atoms. But reality, as it turns out, is far more interesting, because essentially all black holes in the real universe are spinning.
And this brings us to our first major shift in understanding. A rotating black hole, known in physics as a Kerr black hole, changes the geometry of space entirely. Instead of a single point of infinite density, a Kerr black hole actually has a ring-shaped singularity. Research shows that if you enter along the polar axis, so diving straight down the north or south pole, you remain as far away from that ring as possible, which dramatically minimizes those deadly tidal forces.
So here's the absolute crucial point. A human body can actually survive this plunge totally unharmed, provided the black hole exceeds a specific critical mass. Mathematical models calculate that for a human to survive without fatal structural damage, the rotating black hole must be greater than about 900 times the mass of our Sun. Anything smaller than that, and the tidal forces will still tear you apart.
To put that into perspective, let's look at our own cosmic neighborhood. Our galaxy's supermassive black hole, Sagittarius A star, is over 4 million solar masses. That completely dwarfs the 900 solar mass survival threshold. The tidal stress on a human plunging into Sagittarius A star would be less than 0.5 pascals. What does that mean? Well, that's about the same pressure as a small coin resting in the palm of your hand. It is entirely negligible. You wouldn't even feel a tug. It makes our galactic center a theoretically perfect candidate for our journey.
Section 2. The Outsider Perspective.
Okay, before we, the intrepid astronauts, take the plunge ourselves, let's park a mothership at a safe distance and observe a mechanical probe dropping toward the horizon. This is where the physics of relativity gets wonderfully weird. From the outside perspective on the mothership, as the probe gets closer to the massive gravity well, its light stretches out. That's a process called gravitational redshift. To the outside observers, the probe appears to slow down until it's permanently frozen right at the edge of the event horizon, fading slowly into darkness. But the probe itself, it just keeps falling.
Section 3. Crossing the Event Horizon.
All right, let's leave the mothership behind, switch to the insider perspective, and join our free-falling astronaut right in the cockpit of the dropship as we approach the point of no return. Let's map this out. As we move along this trajectory, we experience the visceral milestones of crossing the event horizon. To the outside universe, we're taking an eternity to cross, but inside our ship, the journey takes merely minutes and seconds. We approach the boundary, we cross the 0 point, and boom, we enter an entirely new region of space-time.
And here is what's truly mind-bending. Despite what the folks back on the mothership are saying, our astronaut crosses the horizon and notices absolutely no change whatsoever. If you were to hold a ticking watch up to your ear as you cross the event horizon of a supermassive black hole, the rhythm of your own time sounds perfectly normal. There's no physical barrier, no flash of light, no sudden jolt, just the steady, continuous progression of your own existence as you fall further into the abyss.
However, if you happen to look out the rear window of your spacecraft, the view changes dramatically. The extreme time dilation between the old universe you just left and the new black hole environment you've entered effectively cuts off the starlight. The universe behind you redshifts into oblivion, leaving literally only an impenetrable blackness. You are now entirely, fundamentally, cut off from the outside world.
Section 4. Space and time flip roles.
Now, this next phase involves some cutting-edge physics where the very fabric of reality seemingly inverts. We're looking at what happens to space and time themselves.
When physicists look at the Schwarzschild metric, which is the math that describes the inside of a black hole, they notice that the mathematical signs actually switch. The singularity stops acting like a geographic location in space. It stops being a where and literally becomes an inevitable future event, a when.
To really wrap our heads around this, think of a video game. In the normal world, space is the map you can move around freely, and time is the story that only moves forward. Inside the horizon, this completely flips. Space becomes the locked story. You are forced inevitably inward. Time, however, becomes the map. The interior space of the black hole acts as a dynamic, expanding structure driven by time.
It's a pretty profound thought experiment. Out here on Earth, if I asked you, hey, which spatial direction can you travel to avoid tomorrow, you'd say that's a nonsensical question, right? You can't fight the inevitability of time. Well, inside a black hole, our astronaut cannot fight the spatial pull toward the singularity. Space is now the inescapable current pulling you to the future.
The underlying math reveals a fascinating shift here. If you map out the light cones, which represent all possible future paths for light and matter, they literally shift and tilt inward the moment that threshold is crossed. Every possible direction you could potentially travel points toward the center. All future paths lead down the gravity well toward an Einstein-Rosen bridge, which is effectively a cosmic wormhole.
Section 5. Surviving the Singularity.
Building on all that incredible math, we finally approach the core of the Kerr black hole. Our astronaut has survived the plunge, space and time have inverted, and the destination is straight ahead. Because we entered along the polar axis, safely avoiding the searing heat of the accretion disk and the deadly energy jets, we don't hit a solid wall of infinite density. Instead, we approach that ring-shaped singularity. And mathematically, because of the spin of the black hole, this ring acts as a gateway, not a dead end.
Which inevitably forces us to ask, if we actually survived a plunge and we pass right through the center of that ring, what exactly lies on the other side of this theoretical spacetime gateway? Where do you go when you run out of falling?
This is where the physics of black holes and the origins of our universe totally collide. Some physicists theorize that passing through this Einstein-Rosen bridge drops our astronaut into a brand new expanding universe. Inside this new realm, the singularity you just fell through sits in the remote past, and space dynamically expands outward, a process that looks remarkably, mathematically similar to our very own Big Bang.
Which leaves us staring into the abyss with one final, absolutely awe-inspiring question. If falling into a supermassive black hole safely delivers you into a new, expanding universe, where the singularity is just a memory in the distant past, is it possible that our own Big Bang was simply the inside perspective of a black hole forming in a much larger parent universe? It completely changes how you look up at the night sky, doesn't it? And on that note, we'll wrap up this explainer. Keep wondering and keep looking up.